Firstly, I will say that a lot of these slides, actually, almost all of these slides are from Anton Vardy, the lead developer of Cheetah, data reduction and preprocessing software. He wasn't able to be with us, so I'm giving this part of the talk. This is the main reference for Cheetah software. It is free and open source online, but you don't need to install it. In fact, I would recommend you don't try, because it is heavily dependent on the software and LCLS. So we don't end up taking that raw data, but I'll get to that. So Cheetah and Crystal and other software, when you use it, well, it's all centrally installed at LCLS. There's also support at SAFA, and then we'll use European Excel, Crystal, etc. We already saw this photograph of flat. This is inside the seated fly hatch. So the near next to emission instrument at LCLS, where most of the serial experiments are being carried out. Now, at this side, you can get over 10 to the 12 photons in each pulse, and they are delivered into a pulse, it's an extra beam with a diameter of about 1 micron in one chamber, or 0.1 micron in another chamber. And at the moment, you can't use that simultaneously. So you have to choose the time you use the experiment. The range of temperatures is roughly 5 to 9.5 degrees. We already saw the overview of the delivery, but the reason I repeat this is because the reason for all this new software and all these new approaches is very much the result of the completely new technology that serial experiments involves. Serial delivery of the samples and the fact that we get an individual diffraction pattern, so one diffraction pattern from each individual crystal, and that has to be somehow merged together. Center. The fact that we have femtosecond X-ray pulses arriving at LCLS at a maximum rate of 120 times per second, and as John said, the pulses are 57 femtoseconds long, typically. How do you deal with these kind of intense flashes, 10 to the 12 photons, or even however many million scattered? How do you deal with that and do them out quickly enough with sufficiently high dynamic range? At 120 hertz, because this kind of intensity completely obliterates your sample. But by that time, if you have read out the diffraction pattern, a new crystal has arrived in the interaction region, and a new X-ray is about to do. So this is how we outrun radiation damage, but we don't avoid it. We just don't care. We cannot measure the radiation damage sample. So this poses some unique challenges. One, of course, is the X-ray source. Now, this is not some stable, continuous beam like at a synchrotron. You can really rely on the nuclear. This self-amplified simultaneous emission fluctuates from pulse to pulse. 120 times per second, you get a slightly different spectrum, a slightly different central wavelength, and different intensity. So how do you deal with this in the data? Second is the sample delivery. That's a whole research area on the time. Thirdly, the detector, how do you deal with these new detectors that have to be developed for these kinds of experiments? Fourth is the reason why. So the SFX Data Analysis Pipeline at LCLS is comprised of 3 steps. The first is the data acquisition system, the DAC. Then that controls, that's the control of the user. That is what the beamline operators use to control what's happening in the experimental hatch, and the DAC is in charge of recording all your raw data. So everything that is being recorded, your diffraction data and information measurements from all the sensors that you wish to record, is all dumped into one file, or a number of files, so that it can write out a lot of data simultaneously, but you only have to consider it as one file, and everything's there together in this LCLS format called STC format. So it's got all your metadata that you may want to know. You can even have a measurement of each X-ray pulse spectrum per pulse. We want to have all this information. The next step is what I will teach you to do, which is Cheetah, the data reduction. The next step is Crystal, as you know, and by that point, you will have a nice, clean, reliable reflection system. We're not trying to reinvent the wheel. There's a lot of really well-developed and highly actively developed crystallographic software. But to get to that point, to get to be able to use that, we have to let's deal with this new type of software. So our goal, actually a lot of the, it's not just the bioexpert's goal, but all of the users and all of the developers of SFX initially, our goal is to really make this as broadly accessible as possible to the very broad and very productive crystallography community. So we already covered this, but to give you an example of how much data you can be recording. So the main detector used at CXI is the Cornell Slack pixel array detector, the CSPAD, and it reads that one diffraction pattern is roughly 5 megabytes, which leads to about 2 terabytes per hour if you are recording continuously with a single detector. So after 5 shifts, you have 12-hour shifts, a typical experiment, if you're lucky, is 5 shifts, you can walk away with up to 120 terabytes. Of course, you're never running continuously the whole time. You have to change samples, things can break, but that is a lot of data to deal with. And although data storage is cheaper and easier as we go along, it's a lot of data to sort through, clean, and treat. And then the European XFL will come online, I think we'll be able to use this in 2017. Right. That's a superconducting source that will be recording even faster, because more data. They will not be able to store everything, so they have a lot to learn from CERN, who has to do the data reduction on the fly. You have to throw away some useless data on the fly. Now, I'm here to make sure you don't drown in all this data you are collecting, so the tutorial will be talking about where is your data stored at LCLS, what type of file is XTC, how do I take this data home, and do I really need to take all of it? Anyway, how do I read the file, that's what Cheetah does, and what is next? Now, the same idea of the protocol of the data analysis from the point of view of how much storage you need and how much data there really is. We covered about 2 terabytes per hour. You may end up, let's say, with 4 million frames. Now, a lot of these are shots which miss crystals. So you will never have 100% hit rate. If you are getting a crystal diffraction pattern on every shot, that means your concentration is incredibly high and you have at least 2/3 of your patterns are more than a single crystal hit. So theoretically, with a homogeneous distribution of same size crystals, your best aim is a 30% single crystal hit. I won't dwell on that. The point is, after data reduction, you will be left with a good number is to assume 10%. Often we're running at 2% hit rates and stuff, and that is already excellent because you are collecting a lot of data. And as data analysis, as Crystal and other programs improve, you need less and less, fewer and fewer patterns to get to high resolution. You can work away with, in the olden days, I would say 400,000 hits. Now I can say even 10,000 hits is already excellent. And with good geometry, which I will mention, and I'm sure Tom will mention again, and with a good sample, you can index about 80 or 90% of these. So that's really good. We still need to really, really good structures. As John said, in the olden days, we would need tens to 100,000 patterns. With a lot of improvements along the way from detector geometry and especially the indexing, merging, and evaluating steps, we can now work with a handful of thousand patterns. Now, this doesn't come with LCLS with your user membership. This is the recommendation from very experienced LCLS users. Make yourself a spreadsheet. There is an electronic logbook at LCLS, and a lot of data is stored there. The handiest thing, the best thing you can do for yourself and for other data analysts is to keep a record of everything you've been recording. Now this looks simple and typical, time, how long did you run it for, what sample it was. But you will see online on that tutorial I have made, especially for this workshop, that will be available for the rest of at least bioexperts live. You will see that there are many more columns that you will want to keep track of. X-ray parameters that you change, the sample delivery system, things you change, whether you're changing your nozzle, is the sample continuously clogging, things that you may not have considered from experiments at a temperature. You will definitely need a dedicated logger. And it sounds like a very unrewarding job. There's almost nothing more crucial than having a record of what you've actually recorded. Walking away with 100,000 patterns that are excellent, but you don't know where it came from, except the sample names. Only 10%. So the Cheetah GUI, it's not very fancy, but it's very, very functional. It's running with IDL. You do not need an IDL license to run it, and like I said, it's installed at LCLS. The GUI looks like this, that allows you to launch key finding on any run that has been collected. Now I will say, what is a run? A run is literally the operator clicks start collecting, the raw data stream stop collecting. And because there's a lot of data being recorded at the same time, The longer a run is, the longer it will take to get to the memory that you can access it to. This will make sense a bit later. So typically you have the same sample, as you can see. This says lice. Lice time, you will continuously record many runs of the same sample. But anytime you run out of sample, change nozzle, anything, like the beam goes down, you stop the run. So you can stop conditions, change time delay in pump probe, etc. Okay, the nice thing about the GUI is that it keeps track of the raw data that has been recorded onto the file system at SLS. At the bottom here, you will see, you will be running this GUI, so you will see the font more clearly. In this column, under XTC, the raw data, it says ready, and there's no information along the rest of the columns, because we haven't run hit finding on this yet. So you know those runs are available. You could be working on this away from LCLS, or if there is not enough space in the operational control room, you can be working in the overflow or data analysis room upstairs, but you can keep track of what's going on with the experiment. And all you need to do is select the rows that you're interested in and start running Cheetah, and it will update automatically. It's a one-click process to start the running, and your biggest interaction will be with the Cheetah configuration file. This column is the number of frames it has processed. The number of detector readouts. So if you hear us talking about frames, it does not necessarily mean it's a diffraction pattern or it was actually a hit. So frames can be empty, frames can be whatever you want. So the number of frames processed, detector readout events processed out of that 120 per second, the number of hits Cheetah has found based on your hit finding conditions. It makes an estimate of the resolution, old snapshot, ignore this. It will make an estimate of the resolution, and it'll also keep track of the hit rate. Now, part of your Cheetah output is what we call a virtual powder pattern. It literally sums the intensities from all your hits, and it sums intensities from all the patterns, all the frames you have rejected. So the easiest way to keep track of whether your hit finding parameters are too harsh, whether you're missing important data in your data stream, is to check the virtual powder pattern of the rejected patterns. Now they are not stored to disk. Cheetah's point is to do data reduction. Yes, it's the background correction stuff, but the main point is to reduce how much data you need to handle. So it will only create detection pattern files from things you consider hits and not save the rest. So the only information typically holds from them is the virtual powder detection. You do have the option of saving everything if need be, but I would recommend it. The hit rate reported in the Cheetah GUI is an average over the whole run. And you can also click random hit rate, and it will show you a time, a function of time, how the hit rate has changed. Sometimes you can some microcrystals do not settle in the feed lines, in the liquid jet feed lines. We have a rotation device that follows them, but you can see that if the settling is still occurring, your hit rate will be fluctuating at the same periodicity as the rotation. So every time it rotates, more crystals come up in solution, you can hit them. Every time they settle, they'll probably not be ejected into the path of the X-ray beam. We can also see here, this is a reflection of either heterogeneous sample distribution in your jet. The jet may be wobbling, or it really could be heterogeneous sample quality. You can say, let's say they are distributed evenly. Sample got really good at the end there. Now, as I said, it does an estimate of the resolution. Now, what this is this is a function of pixels, but quite easy to calculate in action, of course. So you can see that most of the patterns were roughly around the same resolution. Now, since I don't know the detected distance for this sample or wavelength, I can't tell you what this means. But that will also show you if you have a heterogeneous quality distribution, and maybe if you have enough data for that resolution later. Another very, very useful check is checking if you are saturating the spots. And you don't have to look at every individual pattern or even too many of them and look at the intensities to see whether you're saturated. Now, the CS pad is reading out 5 megabytes, 120 times per second. You can't possibly deal with such huge fluxes and the dynamic range that it has without, of course, saturating the detector. The CS pad was actually designed for single particle experiments. It has single photon sensitivity, but what we want from crystallography is, of course, a higher dynamic range. But the neat thing is, CS pad has 2 gain modes. So what you can see here, and the next diagram actually shows it better. What you can see here, this is intensity, and this is radius. What is plotted is the intensity of every single peak found in that run. And we set the inner region, this is the radius, so the lower resolution spots. We set the inner region of the detector to low gain, and the higher resolution part of the detector to high gain to effectively extend the dynamic range 7-fold. So these have not been scaled. This part right here, this sharp divide, is simply because these numbers need to be multiplied by a factor of 7. So that's very, very useful as well. So just to summarize, Cheetah is your data reduction. It saves your diffraction patterns, and it gives you statistics. It rates resolution, saves virtual patterns. It can deal with just giving you the radial averages from patterns if you're working with wax, for example. But we will be focusing on zero crystallography. But here is a plot of radial averages. One row is one diffraction pattern's radial average. You can see the mass fluctuations. This could be due to, of course, the sample, or just the thickness of the jet in the line of the X-ray beam. And that's involved with the incoming intensity that, remember, fluctuates as well from shot to shot. You can also have a recording of the spectrum of the X-rays as they're coming in, if the spectrometer is online. It's exact. All right, and of course, you can view the hits that you have found in Cheetah, which we're going to get to in a moment. And they will look something like this. These are the diffraction spots that have been found circled. You can start to see, hey, yep, this looks like a real diffraction pattern. I've got dots in a row. You don't see looms because, I must remind you, this is a laser. So the helix here, the helix here is very thin because the bandwidth is very narrow. It's not as narrow as you would get from a monochromator, which is about 10 to the minus 4. So the 1 on minus 3. The bandwidth is about 0.1% when you're in SASE mode. So it's a very thin slice of reciprocal space. So the number of spots you will see from each crystal is smaller than if it was on a goniometer. The bandwidth is smaller. But the other point is we do not rotate the sample. The pulse is so fast that the motion is frozen. Not just the motion of the crystal, I mean the motion of the molecules, the atoms inside is frozen in those 50 femtoseconds. This is another reason why we need to get really, really good statistics and combine a lot of patterns from a lot of samples, because we simply have not sampled each diffraction spot's intensity sufficiently in a single shot. Now, for verifying whether if your hit finding is running nicely, there's nothing that does better than we are the best system for pattern recognition and any software. Even Google hasn't designed anything that's better than our eyes can learn. So you will have to look at a handful of patterns to make sure you're not picking up too many spurious spots, too many false positives in the water ring or the background, scattering from the cubic phase, things like that. So we will look at them manually. Now I'd like to talk briefly about the detector. It is, like I said, specifically designed and built for the LCLF. And it is modular. And part of the reason is because of the high readout rate. So it's a pixel array detector with 64 components. 2 of them are stuck together, so they move as a rigid body. Each quadrant moves as a rigid body, and you can see here, it's like the eye in the old 007 introduction. move the quadrants apart to open the hole in the center to let the direct beam through. Otherwise, the detector will be dead in 1/120th of a second. Typically, we just leave the hole in the quickest open configuration. You don't want to keep moving this thing because you'll have to refine the geometry every time, just like your plugins. You want to set it up, refine the geometry once perfectly, and you're done. Okay, but it is flexible. Now, the way the data is read out looks, the order in which it is read out looks nothing like the way you just saw. This is an actual photograph of the detector. It's roughly 18 centimeters by 18 centimeters, and it's 1500 by 1500 pixels, active pixels. Obviously, those gaps in between are not active. And you don't have to worry about missing volumes of reciprocal space, because your patterns are from crystals in random orientations. So these little gaps, the spots that you miss from one crystal, you will measure from another crystal. The order of the data readout is again part of the necessary setup to read out some information quickly, but it also means that it's a bit complicated how we rearrange the detector geometry. But of course, all of this is done internally in the software. It's not something you need to worry about. But don't freak out if you open a diffraction pattern and it looks like this instead of what you're expecting to see. Okay, so I'm nearly done with this overview. This is a measurement of, this is after indexing, this is after something that Tom will talk about. But this is actually a heat map . Once you have a decent geometry file and you can index a lot of patterns, you can feed that into a geometry refining program, GeoOptimizer, in Crystal. And it also corrects the geometry for you, but it also reports how incorrect it was. So you can see that these needed a lot of shifts in one direction of the raw data readout, and these needed a lot of shifts in the other direction. We don't need to talk about what fast and slow scans are. But the recipe for getting the geometry file for this detector, which is very important, is LCLS is actively improving these detectors. It's always improving how flat the readout is, with this dynamic range, fixing panels, components that we have broken by having ice events, things like that. So they will give you excellent optical metrology. That's turned into a really good estimate of the geometry file, and then you can refine it to sub-detail accuracy with GeoOptimizer. And the reason I've been talking about this so much is that when this was developed, GeoOptimizer and the program, the precursor to this, we suddenly could improve our indexing rates and of course the data quality at least 5-fold for a lot of the samples. This is a huge, huge improvement. We already had excellent geometry. We already had high resolution structures. But to take it this huge step forward, it's a very, very big development. And the best thing recently is that SLS now has a program where people share their geometry files, which I like as an open source sort of framework. Which means the previous experiment's PI can choose to share their geometry file, so you don't have to redo the work every time you start an experiment. All right, so this is a good time to stop.